Recording in progress. De toute évidence, le reste de la présentation se prend en français, mais il me fera plaisir aussi de prendre des questions en anglais. Ça me fera plaisir de prendre des questions aussi en français plus tard. So today, I wanted to talk not only about 5G, but about the process as well of how standards work and focus on 3GPP and how it evolves and how it becomes a very big system in the end. So I'm going to talk a bit about, whoa, I need to change slide. There we go. Okay. So I'm going to talk about InterDigital quite quickly, but most of my presentation will be focused on how the technical specification work is done in 3GPP. I'm going to say a few things about 5G, but spend most of my time on release 16 and 17 and discuss quite a bit what I'm excited about in release 18 and beyond. All right. So first, let me recognize my employer. I work, as Guilherme said, I've been working for InterDigital since almost 15 years now, focusing entirely on standards research and standards research work. I feel old when I talk about 3G, but this is where I started, and later on in LTE and now 5G. InterDigital is it's a wireless innovation company. It contributes to the wireless and video standards technology. We have one of the biggest patent portfolio in the world related to wireless and video technologies. And when I use my phone, I like to think that I'm actually using some of my colleagues' idea on a regular basis. So we're, InterDigital, you will find InterDigital innovation in every handset in the world today. So with respect to technical specification work in 3GPP, I'm actually going to talk about the standardization itself and how, what are standards, why do we need them, and how do they become a reality. So first, let's go straight to it. 5G, it's a global standard, just as 4G LTE, HSP before that, and GSM even before that. So we've sort of, used to see standards, but if we ask the question, why do we need standards today? Why do we need a standard for wireless communication? I like to answer the question by thinking the other way around. What if we didn't have standards, right? If we didn't have standard, it means that we would have a single company providing the entire system. And that wouldn't make sense from a commercial standpoint. It would just too big to have one company create base station all the way down to mobile. It will also be quite difficult to create new innovation in a system like that, and it will stale the technology. So, it makes total economic sense to have standards because it stimulates product innovation, products differentiation, and so on. But then the question, of course, is what do we need to standardize? What do we need to specify? What is it that we need to say, this is going to be fixed, this is how it's going to be done? Making sure, of course, that we still leave room for product differentiation and improvements in technology. So for 3GPP systems in general, what we need to specify are first terminal requirements. So for example, under certain SINR, I'm simplifying, but under certain SINR conditions, what would be the throughput of a specific device, right? So this needs to be specified. The reason being, if I'm an operator, I'm going to deploy a very expensive network. I'm going to buy a base station. I'm going to buy sites. I need to understand, how close my base station need to be in order to provide a specific service to two devices, right? So that's why we need to define specify terminal requirements. We also need to specify interoperability elements. So we need to make sure that devices from different vendors, they can operate together. Operator network control, we need to make sure that the network is always in control of the device. So we need to specify procedures, signaling, so that operator is always under control. I mean, the device is always under the control of the network. And finally, we need to specify error handling. So what happens in a case when something fails, and how do you recover from these errors? So these are the sort of the four areas where we need to specify things. Anything else than that probably doesn't need to be specified. Probably it can be left for re-implementation. And one example would be, I can give you two examples of things that are not specified. One thing would be On the handset side, it could be, for example, channel estimation. How you get the signals, how the signals are made, or how the reference symbols are created. That is specified because you need to be in agreement between all the vendors and all the manufacturers and how this is done. But how the device takes these symbols, receive them, and create a channel estimate out of it, this is left to UE implementation. Likewise, scheduling on the network side is not specified. That's left for network implementation, and this leaves room for, as you can see, this leaves room for product differentiation. Maybe some UE vendors will have better algorithms than others, and then they can perform better in certain circumstances. Same thing with network operation. So the focus of 3GPP specification work is predictable UE behavior, predictable UE performance, and conformance requirement and testing per device type. Right? So what's important from that discussion is that not everything is specified. A lot is left to UE implementation, and we try to specify the minimum possible. So 3GPP is an important organization because it's the organization that specifies the LTE and then 5G. What's important to understand is 3GPP actually is member-driven organization. So companies like InterDigital, they participate to 3GPP. And then a small technicality, but we often forget about this, is 3GPP doesn't create standards, doesn't make standards, it creates technical specifications, which are then stamped, if you will, into standards by regional organizations. So that's a technicality. The other thing, though, that's very important to understand is 3GPP specify the entire systems, from radio access to core transport network service, codec, security, quality of service. So it provides a complete set of technical specifications which are then transformed into standards, as I just mentioned. And of course, that's huge, right? That's I think if you were to print all the technical specification, you'd have like probably kill a forest or something. There's so much work that has been done that it cannot be done by a small number of people. It's impossible. So there's thousands of people that participate into that work. And it's organized first in technical specification group, TSG. So we have 3 TSG, RAN, radio access network. It's responsible for each of those technical specification groups. They're responsible for a set of technical specifications. TSG RAN, for example, is responsible for the technical specifications related to the radio access network, RAN. That's essentially the interface between the devices, UEs, and base station, and the interface between different base stations. So that's the radio access network. SA, system and service and system aspects are responsible for service requirements, system architecture, and so on. And core network and terminals are responsible for the set of specifications that are relevant for network protocol, core network protocols, and so on. So the work is, in each of those technical specification group, the work is further split, subdivided in what we call working groups. So RAN working group 1. My expertise is more into RAN 1 and RAN 2, RAN working group 1 and RAN working group 2. So most of the discussion will be related to those today. So these groups are responsible for a subset of the technical specifications, and people like, people from my company, they participate into those working group, and the purpose is to create technical specification for the wireless systems. So what's important to understand is, and the thing I want you to remember from this discussion is that first, this is a huge organization from multiple companies. The work is split into smaller working groups. Each working group is responsible for a set of technical specification. And the actual magical work or engineering work has been done in each of those working groups. So how does that work? Right? All right, so I've sort of laid out the big structure here. Let's take a look at a specific time organization. I'm going to discuss a bit how things work. So we have these working groups, and then they meet regularly. So every so often, there's a meeting. There's a standards meeting. It used to be in a hotel somewhere. Now, of course, because of the pandemic, this is happening online. But there's a meeting, and during the meeting, the different working groups, they meet together. like Run 1 will meet in a hotel room, not in a hotel room, in a hotel conference room. Like think of a big ballroom type of things. And then they try to advance the work. The work is split. And there's a way to split the work in different features and so on. And then people, like companies, they send representative, we call them delegate, and they go to the meeting and they represent the company's opinion or ideas. And then there's a discussion, and then agreements are made. Once an agreement is made, for example, at specific meetings, then the work can progress at the next upcoming meeting. So here I think this is 2021 schedule. So we had a meeting in January, then another meeting in April, and another set of meetings in May. And in between those working group meetings, sometimes there's this red box is a plenary meeting. This is where the agreements that were made at the working group level are transformed into are approved. And typically, towards the end of a release, I'm going to come back to what a release is later. Towards the end of the release, the agreements that are made in the working groups, they are transformed slowly into technical specification. And at some point, they become approved by the RAN plenary meeting. So what's important to understand is that there's technical work that's been done regularly. And the technical work is agreement-based, consensus-based agreements. And over time, these agreements are transformed into technical specifications that are later on approved at a higher instance of approval. This sounds like a very abstract idea, but this is how it works. More practically speaking, what this means is every meeting, companies and delegates, engineers, they try to identify new problems and provide solutions for this. And we contribute in the form of a document. We call this a technical contribution, a TDoc. So we contribute to those, we provide these documents a week before the meeting so that other delegates from the other companies, they become aware of it. And then there's a meeting. It looks like what you have on the right-hand side. I like to show this picture because there's a colleague of mine hidden in the picture here. But this is I believe this is a RAN plenary picture of a RAN plenary meeting. And it's always like that. You have a session chair in the front that's directing the discussion. You typically have screens that are projecting some agreements or some documents. And you have a large number of people that are monitoring the situation. They might, the discussion, and they might be asking questions. They might be proposing their own ideas. So you have these technical contributions on the left-hand side that are brought in the meeting. Then there's technical discussion at the meeting. There's some agreements that may be made by consensus or vote. Typically in 3GPP, we operate via consensus. And then over time, this gets magically produced into a technical specification. It's not quite magic. Someone is actually responsible for taking these agreements and transforming them into a technical specification, which is then reviewed by peer companies. And eventually it gets stamped at the end, towards the end of a release, as an official technical specification. Just to give you an idea of the scale of the work of the documents that are being processed, on the bottom of the slide here, I show the total number of contributions per year for RAN 1 and RAN 2. These are two of the most active groups in RAN. And as you see, the number exploded from 10,000 a year to over 35,000 contributions a year when 5G was being at the top of the 5G. So this was like, this gives you an idea of the scale of the work that has been done for specification. So it's a very competitive environment, and not of course not all ideas make it into the standards at the end. All right, so I talked about the release. So release is a set of features that lasts for a period of time. Think of it as a software release, similar to a software release. So 3GPP has a release about every year and a half, approximately. So every year and a half, there's a new release of the technical specification. Why do we use releases? Because it scopes the work and something that's manageable. So we make sure that the work is done within that release time frame. We establish, we do the technical specification, and we stamp them on time. Nothing prevents you from continuing the work in an upcoming release. So the work is split, and then you can continue the work and improve over time. What's important to understand, what to remember is that 3GPP continuously evolved. So even though, for example, when I look at LTE Release 8, even though it was released initially in 2008 or timeframe, it continued to evolve over time. It even got different names. Like LTE was, marketing name was including, typically people would think of Release 8.9. LTE Advanced was probably Release 10.11. Then it was LTE Advanced Pro, and so on, right? So there's a marketing name, I would say, that's associated to a release. And then 5G and R was release 15. But what we don't see in this graph is LTE actually keeps evolving, right? Even though NR started, there's still evolution of LTE. The reason being is if you're an operator, you deploy a huge network, you want the network, your LTE network to survive for a long period of time, and you want to benefit from advancement of technology, throughout the lifetime of your equipment. So of course, now we're going to focus a bit more on 5G and R. 5G started release 15. There was some enhancements in release 16 and 17. And we're completing release 17 as we speak now, and release 18 will start, well, it's already started in some working groups, but we'll start officially in the RAN somewhere around March, later timeframe. So what's important in this slide is the concept of release, the concept of continuous evolution of the specifications. All right, so now that we've talked about standardization and you have a relative idea of how this is done and the amount of work that is required, I'm going to say a few words about 5G, why it's great, and I'm going to say and then I'm going to talk about release 16, 17. So now that we have that, let's move on to the design principles. So a few things, this slide shows what I think are design principle of 5G, and I want to emphasize a few things that remain true today, and then they're a key aspect of what I feel are key aspects of 5G. So one of the principle was to minimize always-on signaling, and this is important because in LTE we had the CRS, the common reference symbol, that would span the entire bandwidth. And that would take energy, even though if there would be no UE monitoring. So the 5G, we got away with this. We remove entirely the CRS, and there's benefits to that because it leaves a lot of this downlink spectrum and uplink spectrum as well. It leaves a lot of the spectrum empty when there's no activity. So the benefit of that is that you can actually it makes it future-proof, right? So if you want to use a network, the spectrum for other technologies, perhaps 6G, who knows, then the spectrum is free to use, and you can still maintain a 5G system, yet use the spectrum for other reasons or future features. So it's very flexible in terms of how you use the spectrum. And then the other thing that I think is very important for 5G, and I'm going to come back to that in a few moments, is the built-in support for beamforming. I like to think of when there's a new generation, I've observed that quite often you take all the features that you develop between the two generations, and then you sort of make them built in the new generation. For example, LTE, in my view, what characterized LTE would have been the built-in support for Mimo, right? We adopted WebDM that enabled multi-antenna and easy support for Mimo. Whereas NR, Mimo is of course a big important aspect of NR, but what I would say distinguishes it is the built-in support for beamforming, in particular with respect to initial access. Now we can do initial access using beamforming, which enables us to deploy NR in very high frequencies. This is a huge distinction from LTE, and all of that together makes it very easy to integrate features in the future, because we have so much flexibility in terms of bandwidth, in terms of spectrum, and in terms of refarming as well, that we can integrate new features quite easily. Talking about new features and enhancement, release 16 and 17 brought a lot of new features in NR. The focus of release 16 was really to support more verticals, and of course, this is all commercial. You want to have, if you're an operator, you want to support not only a broadband for your users, but maybe you want to support other industries. So to diversify your source of revenues. Same thing for network vendors, same thing for handsets or modem vendors. So there was a huge push to support new applications, industry automation, the automotive industry, AR, VR. I'm going to talk about that a bit more later on. Any new verticals that would be going wireless was up for grab. So for that, we need to extend the 5G functionality, and there's a lot of work that was done. The satellite support for satellite integrated access backhaul, which is essentially using a wireless backhaul in band, using unlicensed spectrum, and general efficiency of the 5G system. So there's a long list of features here on the right-hand side that you see for release 16, and there's an even longer list of features that I'm not showing here for release 17 that were introduced. What's important to understand is that each of these features are developed independently and typically it impacts multiple working groups, but they're developed independently in the technical specifications. Yet they can be deployed together. They can be used together, no problem, based on UE capabilities and the needs in the market. So you don't have to, as a UE manufacturer, as a network vendor, you don't have to support all of these features. It's based on market demand yeah, based on market demands essentially. So in the following few slides, what I'm going to do is I chose a couple of, well, a large number of features that I'm going to go through, and I'm going to, sort of discuss the different benefits and the different aspects that were introduced in the future in the release 16 and 17, but I'm not going to make a huge distinction between 16 and 17. So Mimo, I think I joined it when I joined the company in 2007. Mimo work was going on in HSPA, and of course, LT was being developed for Mimo. And I think ever since then, I have never seen a release without some kind of work being done for Mimo. Release 16, 17, and most likely 18 will not be different. What changes from a year-to-year basis or from a release-to-release basis is what new scenarios are becoming feasible and how do we support Mimo in these scenarios. So for example, we had comp in release 10 LTE where it's cooperative multi-point transmission. That was built in R. But the new thing with multi-TRP, so multi-TRP is multiple, is the ability to, for the UE to be scheduled by multiple transmission points, so 2 transmission points. And that enables, for example, better coverage, reliability of higher data rates, for instance. What's different from LTE and NR is these TRP now, if they're operating in very high frequency, they need to support very narrow beamforming. So the procedures for establishing beamforming pairs needed to be reevaluated to support this new scenario. So maybe this was not supported very well in release 15, release 16, 17, we developed we identified this as a scenario of interest, and then we developed the technical specification to support this scenario. So any enhancements, for example, this led to enhancements in beamforming, in beam management related operation. For example, when you have multiple panel on the uplink, on the UE side, for example, or even on the downlink side. One scenario that was studied was the high-speed train scenario. So if you have a high-speed train that travels on a track, one deployment scenario is you have independent base stations, in which case when the train moves from one base station in the coverage of one base station to the other, you have to do a handover. That's undesirable because it requires a lot of signaling. Another approach in this illustrated here would be you have multiple base stations and they're all connected to the same baseband unit. And then you have beamforming that tracks the train as it moves along. That's an interesting scenario, and it requires quite a bit of signaling exchange and improvements on the beamforming and on the beam management side. So this is one scenario, for example, that was studied in release 16, 17. There was other things that were studied or improved, and a lot of these things are very small, but taken together, they make the system much better overall. One example is to support beam failure recovery. So in very narrow beamforming operation and in FR2, for example, the beam might be susceptible to blockage, right? So I don't know, car passes by, you lose the signal for a bit. So that's an undesirable situation. What you wouldn't want to happen is to declare radio link failure when this happens, because it's radio link failure. It takes a while to recover, and it's not the right thing to do if you expect that this will happen often. So there was a beam failure recovery procedure that was designed in release 15, but as I explained, now we want to support more scenarios. And one scenario that was not well supported was a scenario where you have multiple downlink carriers, and then you'd have one beam failure on one of the carrier. Then what do you do, right? So of course, maybe you want to recover perhaps on a different carrier. So these are the kind of enhancements that you see following an initial release of the specifications. So Mimo, what's important here to remember is that Mimo keeps evolving based on the new deployment scenario and new assumption and new technologies. Likewise, power savings, a very important feature. There exist power saving mechanisms where the UE stops monitoring the base station for a while, and there's like a schedule time where you have to turn on and monitor and so on. What they did there is they wanted to go even beyond what was feasible, and they introduced what we call a wake-up signal. It's not exactly how it's spelled in the spec, but essentially that's what it is. So it's a very low complexity signal to decode, and the way it works is you turn on to receive as a UE. You turn on to receive that signal at a specific point in time, and if you receive it, then you turn on the rest of your radio to receive your actual grant. So what this enables you to do, and of course that's not specified. That's an example where the standard, the specification specifies a signal or something that you can use on your hardware to do something else. So in this example, you could build, for example, you could build a specific receiver for just that wake-up signal. Once you receive and you identify that you receive a signal targeted to you and that wake-up signal, then you trigger internally in your modem, you power on the rest of your receiver that takes more battery to receive the more complex control signal, in this case, the PDCCH. The PDCCH, actually, it's an interesting control channel. This is where you receive your control information that will tell you, expect to receive data in this, at this point in time, in this frequency over these resources, or it will tell you when to transmit. But to decode the PDCH is quite intense because it requires some blind decoding. So it's a very power-hungry channel to decode. So that's how, and one improvement in release 1617 that was introduced was this wake-up signal, and it enables a UE manufacturer, if it supports it, to potentially save quite a bit of power on the UE side. Maybe that's not so important, maybe for a handset, but for industrial application or sensors, maybe that becomes more important. Big feature in release 16 that was introduced was NRU. That enables NR to operate in unlicensed spectrum. The unlicensed spectrum is essentially, it's attractive because it's free. This is what your Wi-Fi modem at home is using, for example. But then there are restrictions, right? You have to share the spectrum. You have to follow the regulatory aspects. So there's some listen before talk mechanism that need to be introduced. There's also some requirements on how much bandwidth you use in order for the other devices to detect your signal. So there's a lot of things that are non-native to NR that needed to be specified in order to support NRU. But it's quite interesting because in NR, as opposed to LTE, NRU, you can actually deploy a standalone network, NR network within a licensed spectrum. This is a new feature. It's not limited to that use case. You can always use a more typical use case would be a network operator using unlicensed spectrum when available to offload data from the network, from its licensed spectrum. Of course, the problem with unlicensed spectrum is that you cannot guarantee quality of service. Right? So it's free, but you cannot, well, it's free to use. It's subject to interference from other devices using it. You have to share with other devices. There's coexistence issues. And you cannot rely on it from quality of service perspective, but then you can use it to offload from time to time. Positioning was a big topic as well. This is an interesting one because positioning always existed, or for a long time existed. there were requirements, for example, when you make a 911 call, for the operator to be able to indicate to the emergency services a rough position of where the call was originating. The positioning technique that are used in 3GPP is a combination of GNSS and AOA, AOD, time of arrival, and so on. In release 16, they targeted a very stringent, like 3-meter indoor and 10-meter outdoor positioning accuracy. So it was targeting regulatory and the commercial use cases mostly. And then in release 17, they target even more advanced use case, and that's more for commercial and industrial application. And then they target like very stringent positioning accuracy. For example, like less than 20 centimeter for IoT. This is 20 centimeter. It's a very, very precise positioning mechanism. And to do that, they had to look at every part of the system. And for example, they studied the timing error between when you receive the signal to where it's actually being processed. So the whole processing chain can be now taken into account in order to achieve these very small accurate positioning. There will be even more positioning work that will be done in release 18, for example, with the side link. So positioning keeps evolving over time. It's an interesting feature. It's an interesting service that can be provided by operator. Another very interesting service or a feature in release 17 was a non-terrestrial network, so the satellites. What's interesting here is that instead of having a fixed, the way I look at it is instead of having a fixed terrestrial network when your device, you move from one cell to the other, now you have the entire network that moves around you. So that brings interesting problem, for example, with handover, because then you have a handover that happens very regularly. As soon as a satellite passes by, you have to hand over to that satellite. In order to solve that problem, you don't want necessarily to send handover signals all the time, because that would be quite heavy on the signal inside. So in order to solve that problem, a handover mechanism based on the observation that the satellite movement is predictable was designed. So based on the location and time, as a device, you switch to another satellite in a predictable way. Right? So that's one way it was solved. Another problem that was solved is for initial access, for example. You need to know the rough RTT between you and the base station and the satellite in this case, in order to make sure that you send the signal at the right time so that it's received properly. And then, of course, as the satellite moves, this RTT changes quite a bit, right? Because it's not the same distance when the satellite is at the horizon as to when it's at top of you. So there's a mechanism that was introduced to estimate the time delay and compensate for it on the fly. So these are the kind of changes and features that are added to the specification in order to support very advanced use cases like NTN. There's also NTN was particularly difficult because, as you can imagine, there's a lot of timers that are fixed in the technical specifications and need to be that were designed based on a terrestrial network, and that to be increased, and all of the timers had to be, and counters and so on had to be revisited for NTN. So it's a huge amount of work right there. URLLC, that's an interesting one because it opens the door to new markets. I mentioned industry application and automotive application and so on. URLLC is one of the features that involves a lot of small different things that's added to the technical specification. I'm going to give you a few ideas of the kind of features or functionality that's added. One functionality that was added more recently is the ability for the network to actively stop a UE from transmitting. So a UE gets a grant, but then the network realizes that maybe another UE should have priority. So it sends a signal to that first UE to essentially stop that UE from transmitting. So that's sort of a proactive transmission, preemption scheme, for example, on the uplink. So that's one feature that was added. Data duplication. So to achieve higher reliability, you need to transmit data. You need to duplicate the data and transmit it across different different channels, I would say. So data duplication existed before, PDCP duplication existed, but then based on the new scenarios with multiple TRP, they actually increased the number of legs from 2 to 4, right? That sounds trivial, but then there's a lot of work that needs to be done in order to make this happen. One aspect that's interesting is non-public network. So that's, I put it here, it's not necessarily related to URLLC, but a non-public network allows you to deploy an R in non-public way, right? So essentially, non-operator. So you might be, I don't know, factory operator, mining company, and you would deploy your own network that would be only visible for your own devices, for example. Couple that with NRU, operating in unlicensed spectrum. And I'm not saying products exist today, but this is something that could be feasible. Then you can have a company, like a mining company or a factory or something, that deploys its own private network in unlicensed spectrum and may be able to use some of the URLC services or some of these services to operate its machinery or whatnot. So as you see, we've gone from a system that was largely designed for providing voice calls like basic broadband services to more advanced broadband services to now a system that's available to commercial use cases and large-scale deployment for very specific applications. The benefit, of course, is that you can all use the same baseline standards and thus the same off-the-shelf components to build your solution. Very cost-effective. Lastly, for release 16, 17, V2x. So we've had Cellular V2x in 3GPP before in LTE. That was supporting basic safety and also some advanced use cases. The difference in NR is that we're going above that. And then we support now unicast communication, so a more efficient direct link between cars. And also you support multiple QoS services. Layer 2 relays are also being introduced to have enhanced coverage. And in general, we've gone from sidelink to support very specific use case, so V2X, to a sidelink that's generic enough that can be supported in future releases that can support other features in future releases. So I think the sidelink will evolve over time to support more than just V2X applications. All right, so that brings me to 5G Advanced, which is essentially our release 18 and beyond. So what I need to say is in the RAN, the radio access network, the work for release 18 has not been settled yet, so we don't know for sure what will be in release 18 and beyond. This will actually be done or agreed in a few weeks. There's a December plenary that's coming up in second week of December, I believe. Well, in the meantime, what I thought I would do is I would present, I chose a few features that I think are interesting, not just for release 18 perspective, but maybe for a longer time. So features that I think will evolve over time, a bit longer. But first, what we feel should be the key focus for 5G Advanced is supporting key use cases like XR, automotive, reduced capability device, going even further down the line of extreme capability. So from low capability device to very high capability device. Higher frequencies, we want to see the side link to be more used for enhancing the coverage and even improve the spectral efficiency. Improve support for new device architecture application. I'm going to talk about XR quite a bit. Wearables, cloud gaming, all things that will need to be supported. And improve support for AI ML applications. I'm going to talk a bit about that for verticals, and also not only for verticals, but also for system enhancements and also for physical layer enhancements. So I'm going to spend some time on XR and AI ML because I feel that those are very interesting, and then it will probably last beyond release 18. But then, of course, there's other topics that will be addressed likely in release 18. Mimo is one. And then you can see there's a lot of different topics that we feel will be addressed. There's some of them are continuation of existing topics. Others are new topics like UAV, cross-division duplex, collaborative terminals. These are new topics. And then XR and AI ML would be two topics that I chose that I think are very interesting and they're worth discussing a bit more. So extended reality. So extended reality essentially includes augmented reality. So this is the glasses where there's information that's added on top of what you're seeing. Virtual reality, that would be the headset where you sort of see a virtual world, and mixed reality where you can you have additional tactile information, and it's a mix of real of augmented and virtual reality. So that together is what we call XR, extended reality. And of course, that has many applications. Just let your imagination go. We can think of healthcare, military, of course, industrial, a lot of entertainment probably. So it goes beyond gaming, essentially. There's even retail that could be interested in that. So if, for example, you put a pair of augmented reality glasses, as you scroll down to the aisle, maybe you're searching for a product, it appears, it makes it flash or something. So we can think of all these applications for extended reality that will become real in a very short time. The devices have been evolving for a bit. There was the Sensorama in the early 60s. That was probably the first immersion type of device. But of course, now we have more practical devices such as the Oculus Quest, for example, that exists today. We have other glasses, other type of glasses for virtual and also for augmented reality that are in the market as prototypes or even as product. The Google Glass could be thought of one augmented reality type of device. And then over the future, we're going to see other immersive type of devices like haptics, thermal sensors, for example, or not sensors, but thermal, actuators, I don't know how to call it, tactile experience on the entire body, olfactory as well, immersive devices. So these devices, we can expect at least some of these devices to make its way into a product market in the close future. And of course, in order to be useful, they need to be untethered. Like you don't want to carry a cable around. So of course, a lot of these devices will require some kind of wireless connectivity, and we think, of course, that NR is well suited for that type of application. So 3GPP has been studying some XR form factors already, and as you see in this graph, you have on the top you have the virtual reality type of handsets and the augmented reality type of handsets or glasses on the bottom, and then it ranges from early on. Type of devices was essentially is based on your phone, on your handset that has all the XR capability, the modem, and the location capability, to a more complex device on the right-hand side that has maybe like the glasses with the 5G modem in it, the XR engine, and maybe even the tracking capability inside the device. So it goes from anywhere between full no handset, very crude devices to something very advanced, and in the middle we have mid-level devices that have no 5G capabilities and perhaps no even XR capability. So those capabilities are in your handset or in a device that you carry with you. So all of these form factors are susceptible to appear in the market, and these are studied as potential devices that we will need to support. In terms of the work will start, of course, in SE to establish QoS requirements. And one of the things that needs to be done initially is, and one thing that we realize is that the existing QoS model that we have, they're not optimal when addressing these high-end scenarios. One of the examples I can provide here is this exclusion zone scenario, where you have a local site where you have a worker perhaps that has some devices and some audio-visual elements. There could be a surveillance camera on site and maybe an alarm and so on. All of these are are communicating via 5G network to a centralized location remotely, where could be someone that supervises the worker and wants to make sure that the worker doesn't get into trouble, into areas that could be dangerous. So that could be like a mining, a factory, that could be anything you can imagine. So all of these signals and all of these services, these applications, they are carried through currently, they would be carried through independently over a 5G network. What we want to happen though is we want to have to be able to support a quality of experience that encompasses all of these different streams. And that doesn't exist today. Like we don't have the ability today to formulate different, like link quality of services between applications together. They're all independent. So one of the potential study for release 18 would be to look at enhancements for the Qos model to support these type of applications. So that would be the starting point. And from there, you can define, from there, the requirements of the Qos will trickle down to the RAN, radio access network. One aspect that we study, for example, enhancement for the RAN and the radio access network for XR, we studied aggregating videos and applications together. And then one of the studies that we made, one of the simulations, deployment scenario that we've had, we noticed, for example, that not surprisingly, that the uplink was the limiting factor in this case. Of course, that's not surprising because you know there's you know power limitation and so on that's associated to the uplink, and there's also standards limitations in terms of capabilities for the uplink that's not there for the downlink. So not surprisingly, we will need to enhance the uplink quite a bit. Also because in previous systems or previous use cases, the applications were mostly downlink heavy, right? Whereas now with XR, with processing that may happen on the edge or on the cloud, there's a lot of data that will need to be sent on the uplink. So maybe with XR, we're moving towards a more balanced uplink downlink type of scenarios, which will require improvements on the uplink capability. So in details, what this means is for release 18 or for potential release 18 work for XR, we could imagine that would be work done on QoS differentiation, synchronizing the transmission between multiple data streams, right? So we have same application, but different data streams. They need to be timed together so that it makes sense at the other end. Power efficiency, there's new traffic characteristics. There's new traffic that's been that exists for new traffic type, new traffic data traffic characteristics. So perhaps the power efficiency will need to be revisited. RAN awareness of XR application, UE being able to tell the network, give the network more information about the traffic type, the type of application, in order for the network to be able to meet the QoS. That doesn't exist today. And then support for extended coverage, capabilities, and mobility for XR, the typical wireless elements that we need to improve. So that would be for XR. The next one is AI/ML. That's a bit more complex. It's very non-traditional. So what I'm asking, the question I'm asking here is, what is the impact of AI/ML for 5G and 5G advanced? On the specification. So we have AI/ML exists. We can use AI/ML to optimize some functions already that would be transparent to the technical specification. What is unclear is what needs to be done in the system, maybe to help these applications, or how will the advancement of AI/ML, maybe in the handsets on the Node B, will impact the technical specification. What kind of work do we need to do there? So first application layer. So applications are using AI/ML today. So that's transparent to the 5G network. So an application, but then there's still impact, right? Applications may need to transfer a model from one end to the other. In which case, what are the requirements? How much data are we talking about? What are the reliability requirements? How often is this transmitted? What are the delay bounds and so on? So this needs to be studied because it may impact how we design the system, and it might trickle even down to RAN level requirements. Another aspect that may impact the system quite a bit is how do we enable transfer of AI ML data over the network, sensor input, exchange of information for training and things like that. It has a specific traffic characteristics. We need to make sure that the current system is well designed for these things. So that's the first aspect. And then on the file layer side, that may be quite interesting for researchers that are in this area as well. AI ML, of course, can address a number of, it's a tool. It can be addressed. It can address a number of use cases, problems, optimization, including Mimo feedback, overhead reduction, for example, of resource of reference symbols, beam management, position and enhancement. So these are all different problems where we think AI ML could help in optimizing. The question, of course, is how is this going to play out? How does this play out in terms of standardization? Before we answer that question, we need to look at different possible models of AI ML and how it would materialize in practice. So I categorize like 3 different AI ML models. The first one is the AI black box. Essentially, you have an AI black box. It's an optimization block. It's in the chip of a modem, of a UE or a G-Node B, and it's completely transparent to the network. Perhaps that AI ML engine is solving is optimizing for a very specific problem in the UE or in the G-Node B, and it's transparent to the network. There's no need for the specifications to be involved. It's completely out of scope of 3GPP. Maybe there's some feedback and so on that's used, but mostly independent. Right? So that could be today. You can have that. You can have an AI model that implements, I don't know, channel estimation or beamforming management, and that's completely transparent to the 3GPP specification. Another level would be where you have a UE-based AI black box, in which in this example, you have a UE that is known by the network to have AI ML capabilities for solving potential, to enable or to execute certain functionalities. So in that case, the network knows that the UE has specific AI ML functionality, and then maybe the specifications, the requirements in the specification is to be able to control the module, capability signaling. So, how do we know that the UE supports this? What kind of AI functionalities or capability each of these blocks have? Then it could be signaling for the network to configure these AI blocks, and so on. So we can imagine some kind of awareness of the network, and this is impacting the specifications from the signaling standpoint, configuration, control, and so on. And then finally, there's this more complex use case where you have an AI model that actually spans across the wireless medium. So in this case, obviously, because it spans multiple devices, it needs to, the system or the 3GPP specification need to be aware of it. Then it brings the need for new signaling, new configuration, perhaps model definitions, perhaps exchange of data for training. So the whole processing chain needs to be specified in some way. So these are the 3 different ways we feel that AI can impact the specifications, from almost nothing to completely implementing a functions. Like the last one could implement an entire functions on both sides of the modem. So how do we do that? Like, how do we standardize this? Right? How do we process that? So the first challenge, there's a number of challenges associated with that. First is what data sets are we going to use for model training? This will need to be agreed. The second challenge would be, how do we define the UE capabilities with respect to AI processing? Right? We'll need to agree on that. There will need to be some functionality that are defined in terms of memory, maybe processing power, latency. So that's the second challenge. Of course, then we'll need to worry about interoperability. So how I want to make sure if I have an AI engine in the UE, I want to make sure that it has it meets certain requirements, and I can train it in a specific way. How do we evaluate AI-based solutions, right? It's new methodology that we don't currently have. And how do we guarantee a predictable performance of AI module? These are all the things that are challenging from a specification standpoint, and we don't really have answers to that at this point. So release 18 coming up. We expect that there will be work, at least study work, that will be done in AI ML. The first thing that we think should be done is identify the use cases and the scenarios for AI ML, study and define the evaluation methodology. We need to be able to evaluate it. We need to be able to measure it. So this will need to be studied and agreed on. And finally, study and characterization of the UE capabilities and so on with respect to the AI model. So hopefully the work that will be carried out in the SI is conclusive, and then we would continue in our release 19 with a work item, perhaps with a first set of technical specifications supporting AI ML for physical layer. All right, so this would be the next step in the specification work. All right, takeaways. We're almost done. We come to an end. I guess what I want you to remember from this discussion, I've been talking quite a bit now. First, coming back to the early discussion is the first thing I want you to remember is technical specification work for 3GPP system. It's a large industry consensus effort that involves thousands of people. The 3GPP specifications, they continue to evolve for a long period of time, right? So it's not because 5G exists that 4G stopped evolving. It will continue evolving for at least a few releases from now. And finally, we're at the beginning of a new specification work for 5G Advanced. And hopefully, I convince you that we'll support exciting new use cases and technologies such as XR, AI ML, and there's even others that in the interest of time, we could not really cover. Right. So hopefully that was, that's all I have, prepared for you today. I hope you enjoyed it. Maybe we have time for questions or.
Yeah. Thanks so much, Dr. Benoît. We really liked the presentation. It was very, very informative for us. I do have a few questions here. I will start with one of myself. So basically, we see that from LTE to 5G radio, there wasn't a breakthrough technology. Basically, they continues using OFDMA and possibly 5G essentially brought more flexibility to what we have in LTE, right?
Right. This is well, okay. We've been using the same waveform. That is true. I don't like to define necessarily a generation with respect to its base waveform only. I know this was done in the past, but the key point here, I think, is a change of. There's a lot of technology actually that we don't see in 5G, and that's probably that lack of visibility or lack of a big thing, right? That makes it look similar to LTE, but it is much more optimized for the use case you want to support, right? So it has a much more a larger capability at supporting wide use cases that LTE was just not able to do. And it's not just a specification aspect. There's also a technology aspect. If you think of millimeter wave, for example, polar coding. So there's a lot of technology elements that were introduced that are being used in 5G that were not really used in NR, or could not be used at the time of NR. Sorry, of LTE.
Yeah. So yeah, my question was, do you see that changing in the future releases, or the future generations, or are we going to stick with the OFDMA?
So with respect to the waveform, there was a lot of work that was done early on in the study item for 5G NR, that where multiple different waveforms were studied. The consensus was at the time that at least for lower frequencies, there was no real benefit of using a different waveform than OFDM, because with the added filtering, it was feasible to get a very band limited signal. So the other waveforms that were studied at the time were not so interesting from that perspective. Having said that, we might see applications in the future. Like, okay, first we might see that going in very high frequencies, that will need to be revisited for various reasons. OFDM might not be the best waveform to use in very high frequencies because of hardware limitations, for example. Another use case could be very low capability devices. Maybe it's not interesting for low capability devices. So I don't think there's a fixation on not using something else than OFDM. I think it's use case based. It's based on use case, technology, and what makes sense for the particular scenario that you're considering.
Thank you. So we have another question, which of the new 5G applications are considered for release 18 and beyond? Would you say that is the toughest in terms of technical requirements?
I mean, in my view, I think this is my own view. I think XR is very much demanding in terms of technical requirements for many reasons. The latency, right? Because you need to have, when you move your head in a VR headset, you need to have very, very tight requirements on the latency. That's very stringent. Power-wise, it's very stringent. The bandwidth required to support this application, the fact that it's uplink as well. So I would say that's probably the most demanding application that I'm seeing right now on the more consumer electronic side. And of course, on the industrial side, I don't really have a view on this necessarily because I'm not an expert on industrial application, but I can imagine that there must be some industrial application that could be very, very demanding from a requirement perspective. But from a consumer electronic perspective, definitely, I would say that XR is probably one of the most exciting and most demanding use case out there that I see for release 18 and beyond.
So the other question is, what's your take on the Open RAN, and if you see a place in it for 3GPP standardization? Is it something considered for coming in future releases? And if not, how do you collaborate with Open RAN community in this case?
I mean, Open RAN is more of a implementation aspect, not so much of a standardized aspect. I mean, I'm not too familiar with what Open RAN does, but my understanding is that it's more competing with ORAN is more competing with existing products on the product side rather than the standardization side. Where will there be products out there based on Open RAN that hit the market? We'll have to see. I'm not a commercial expert from that perspective, but there could be.
Yeah, if I can add, what I see is, for example, the Open RAN defines the splits, and for example, the split 7.2 came up to the specification, I think, on the release 15 or 16.
Right.
So yeah, that's all I know about the Open RAN. So another question that I have, so for 5G, one of the biggest constraint that we had before was the spectrum. So 5G came and brought a lot of spectrum with the use of millimeter wave. So right. Which is the biggest constraints for the next generation?
Oh, that's a good question. I wish I knew that. So I mean, spectrum is always a big constraint. Mm-hmm. I mean, this is like some people say God does not. You cannot create more spectrum, right? It's just. Mm-hmm. Yeah. Having said that, the constraint might be business, right? I mean, we have a lot of spectrum if we can, split it in a small way, right? We have very small cells, right? So then there's the constraint might be business, financial more than technical at to some extent. I mean, another way of saying it is we have a lot of technology that exists today does it make economic sense to provide services that we want everywhere? That's another question. Mm-hmm. So maybe the next challenge, I mean, there's a huge technical challenge. Some of it, I would say that for commercial adoption, some of it is not only technical, but some of it is business oriented, some business side. Can we make money with this? At the end of the day, someone has to pay for this.
Okay. We have someone who raised their hand. I don't see their name, but I'm gonna, let me see. Next student. I think he can ask his question.
Yeah, hello, thank you for your time and presentation. Thank you so much. I have a question regarding the challenges. I think for release 19, you mentioned the predictability, the prediction. So for the current 5G, is there any predictability using currently, either by user behavior or traffic? I mean the traffic or the data prediction?
So, okay, so the question is, yeah, I mentioned predictability being a challenge for implementation or using AI/ML functionality in the physical layer. Well, today, I mean, one aspect of standardization is to have predictable UI behavior because it needs to be predictable because you want to be able to control it. You deploy a network, you spend billions of dollars on spectrum, on network equipment. And then users are paying for your service. They expect to have some quality of service, and in order to be able to deliver that quality of service, you need to make sure that the device that's at the end of the line is behaving exactly as you expect it to. So that's the predictability that I'm talking about. The question with respect to AI/ML, and this hasn't been, you know, this is a challenge. Today, the way we're building algorithms and the way we're building functions is by, you know, coding them in a very specific way. So, you know, technically speaking, we can predict ahead of time, given a certain set of input, what will happen. With AI/ML, it's training based. So under some conditions, we might not exactly know for sure what will be the behavior of the device. Is that a problem? I don't know, but this is something that we need to ensure that that is not a problem. Does that answer your question?
Yeah, thank you.
Welcome.
Thank you.
That's a very good question.
Claudio, you gonna ask something?
Yeah. Okay. So during the beginning of your presentation, you talked about how new technologies are added into new releases. But there's something that we, I think, as students don't understand. Like, we're doing our research in a master's program or in a PhD program. How does our research reach these releases, if they ever do reach? Like, how do our contributions make it to new releases?
That's a very good question. That's a very, very good question. So multiple ways, right? Multiple ways. So some of you might be researching. I keep using the channel estimation example, but you know, new coding scheme, new algorithms for, you know, new AI/ML algorithms for doing things. So how this is going to play out eventually is either on the product side, implementation wise, right? So maybe you'll never see it in the standards, right? So maybe if you work on a very smart scheduling algorithm, it's not going to be specified, but maybe someone will use it in the future in an implementation, right? So it might not be visible, but it might be used, right? So it's not because it's not in the technical specification that a technology is not being used, because not everything is specified. So that's the first thing I would say. The second thing I would say is that sometimes, in order to enable some new technologies, I'm thinking AI/ML here, there might be a need to exchange new signaling, right? New signals, new measurements, right? So that's one way. You know, should some of you design or, you know, discover a new way of doing something that requires a new exchange of signal, that at the baseline requires exchanging of signals, then you might not see the algorithm itself. Maybe that algorithm will be in the network or implemented somewhere else, offline or in some way. But then you might see it might appear in terms of exchange of signals, because that's what's visible for interoperability perspective, right? And lastly, you know, once in a while, there's a new coding scheme, there's a new that materializes, that is discovered and makes its way into the standard. I would say that the more fundamental the discovery is, the longer it takes to get into the standards, because it needs to be tested, it needs to be implemented in various prototypes, and it takes time to get into the point where it's recognized as a good technology or as a stable technology to make it into the market. Remember, these things are, you know, a modem costs millions of dollars to develop. Same thing on the network, like tens of millions of dollars to develop. So it's you don't want to go into an endeavor before you have some proof that you know, via maybe prototypes or very recognized contribution, that something is worth investing that much money. So there's like multiple ways, right? So first, implementation wise, you might never see it, but someone might be using it. Maybe there's an impact on the system that requires exchange of signals, and maybe if it's very fundamental and it's going to take years to make it into a product, perhaps maybe the technology is not there to in terms of processing power, and then it's going to take some years to make it into visibility into the standards. But it's not because it's not visible in the standard that it's not being used, because there's some aspects that are not specified. Most aspects are not specified. Does that answer your question?
Yeah, it does. Thank you very much.
Because that's a misunderstanding, right? It's not because it's not specified that it's not being used. It's not because something is, I'm thinking about scheduling algorithm. A lot of work was done in scheduling. The question is always, is it possible to use that with the existing system? Do we need to modify it? Quite often it's not, there's no modification that's needed to implement a specific technology.
Yeah, it's like if it doesn't get used per se, someone's being inspired by this work to do something else that will be probably included in the release.
That's also a possibility, right? Your new schemes, your discoveries may inspire your principle. The basic principles might inspire other, you know, other people to create other technologies based on it, and that could be also an impact. So I mean, there's multiple impacts that you can have on the system, and the issue, of course, I mean, not the issue, but you know, you researchers, and I hope you're not doing this for the fame, but you might never realize if your invention or your ideas are being used.
Yeah. Okay. So
and
keep doing it.
Sometimes takes time as well. I see, for example, the IRS, the Intelligent Reflective Surface, that has been in academia for like 2 or 3 years. I think it's being studied for the release 18. Yeah,
there are proposals to study it, and that's probably the fastest academic to specification topic that I've seen in my career. If you think of OFDM, it was invented in the 60s, right? Just, you know, and then 15 years ago, it got into the standards, because this was the constraint there was more signal processing based. So it depends on what the constraint is as well. Like not the constraint, but it depends how big of a challenge it is to implement it. That's why you have to see prototypes first. You have to have some kind of proof that it can be deployed in some predictable way, in some stable way.
I think we have another question for Niloufar.
Hello everyone. Thank you for your presentation, Dr. Benoît. And I had actually 2 questions. The first one is that you mentioned robustness. We know that with coming 5G, the size of the cells would be smaller because of these properties of the millimeter waves that 5G uses. So for sure we have a lot of interference rather than the 4G and LTE networks. So and I saw in your presentation that you mentioned robustness. How you implement this robustness in 5G networks? This is my first question.
So in terms of, and that's a good question. Robustness, reliability, right? So first, with respect to smaller cells and millimeter wave and very narrow beamforming, I'd have to refer back. My brain tells me, my recollection tells me that interference was not as much of a problem as we initially thought because of the smaller beam, but I'd have to verify that. In terms of robustness, there's a lot of elements that are in the system today, even as of today, in order to be able to avoid. There's two things. There's interference management, there's the robustness. So I'm going to talk about interference management. So the first element of interference management would be there are elements in the system that enables a base station to tell the other base station, by the way, I'm going to use the following. I'm going to transmit in these next few resources. Please avoid doing so. Right, and then the other base station will say, "Oh, okay. If I'm going to avoid these because it's going to create interference." So there are mechanisms that exist today that can be quite fast and quite effective in managing interference from the network perspective. There's also there are some mechanisms that are existing today from the UE side to measure interference dynamically and report to the network. For example, there are mechanisms where, as a device, I can measure interference from other network other base station, and report it to my own base station, and my own base station may make a decision to schedule me where the time and frequency when there's no such interference, or expect that there would be no such interference. So there exists a lot of advanced mechanisms to avoid to mitigate interference. With respect to reliability, reliability, then you have a few tools at your disposal. Most of them are based on repetition because our diversity. So, for example, and then of course, then you cannot have reliability and spectrum efficiency, right? It's a trade-off, right? You cannot have both. I mean, you can have both, but there's a trade-off that needs to take place. So one example of a reliability mechanism is to repeat over time. So you transmit and then you retransmit over time. Another example is to have a data duplication, but on the different bands, different frequencies. So these are all tools that you have at your disposal, that the network has at its disposal to, in order to trade off interference, reliability dynamically.
Thank you for your answer. And my other question I wanted to ask is, you several times mentioned in your presentation that we want to support Mimo. So what are the limitations that we have for applying like Mimo? Like, we know that the benefits of Mimo, it provides us with a high gain, but what are the limitations?
Right, no, that's a good question. So, like, over time, in my career at least, Mimo evolved. Like, Mimo evolved over time, in a sense that the number of scenarios and use cases over which Mimo could be used in the specifications increased. One of the basic limitation of Mimo is the CSI feedback, right? So I cannot use an unlimited number of antennas because I would need to have an unlimited number of reference signal to measure the channel. So that's a fundamental trade-off for Mimo. I would say massive Mimo, for example. Then there are physical constraints or practical constraints. For example, we could have antennas everywhere in space, right? But then you need to connect the antennas together. And when I say connect the antennas, is a bit more complicated than just putting a cable, right? Because you need to have a receiver, right? And A to D converters, and then this needs to be all synchronized together, and all this data has to be coming at the same spot to be processed together. And then there's limitation with respect to cabling. There's limitation with respect to speed of light. And signal traveling through those cables. So there's like constraints like this that makes it that we're limited in terms of number of antennas, where we place them, and so on. So there's like practical limitations with MIMO. Then there's signaling limitation with respect to what makes sense. At which point does it no longer make sense to measure all the channel in order to make a decision for multi-layer MIMO and so on. And then finally, there are some limitations with respect to the channel themselves. So some channels are okay for a couple of layers MIMO, but maybe not for, even if you have 1,000 antennas, maybe you won't support because the channel does not have this nice identity matrix characteristic, and maybe it doesn't make sense to have, I don't know, 20 layers MIMO, for example, right?
Right.
So you have a lot of constraints, and every year and a half, every new release, right, we tackle a new constraint, right? So for example, multi-TRP is one constraint that was tackled recently. So we add the scenario where we're assuming that we have the transmission points that are far away, yet they have a fast enough connection link between each other, ideal backhaul, that we can do processing. So that's a new MIMO scenario that we enable with the specifications, because we're making an assumption because of technical feasibility of that scenario. Then we advance forward step by step.
So my question is, despite of all these difficulties that we have in finding the channel state information, I wanted to ask you this question. Is it worth it to use MIMO, just looking at the benefits, pros and cons?
Well, there's you end up finding the right, the sweet spot in terms of cost benefit, right? Always. MIMO is very useful. There's a lot of work that's been done on MIMO, on multi-user MIMO, for example, where you have a device where the network can transmit to two, using the same time frequency resources, to two devices at the same time, right? This is one scheme of MIMO that does not require one terminal to be able to treat two simultaneous streams, but it's distributed across two terminals. So that's one example of a very useful MIMO schemes and networks today.
Thank you for your time and for your answers.
Welcome. And also we have to make a distinction. There's multi-layer MIMO and there's also beamforming, right? We have to be a bit conscious of all these different aspects, right?
I see. Yeah. Thank you.
Very useful. No question.
Thank you.
Any other question?
I have follow-up regarding the data set. You have number one challenge for release 18. So is there any way, could be a data set available for some, like if we have some scenario algorithm or we need to apply it for some data. So do you think could be available for a research, like a real data set?
Well, for research, that's one thing. My concern, the challenge I mentioned was mostly for a standardization aspect, right? Because we will need to agree, different companies. The challenge is for different companies to agree on a common data set, or whether it's needed to have a common data set for training. That's a challenge that will need to be resolved in the standards. I don't know how this is going to play out, to be honest with you. I don't exactly know what would be the right way of doing this. As you know, data sets, if you want to play the AI ML game, the key is the data. We can generate synthetic data, but then this is just as good as synthetic can be, right? One thing that may happen, and this is, I'm just imagining one potential outcome in the future. One thing that can happen is that 3GPP agrees on a way to generate synthetic data, and that resulting data might not be shared, but the way it's generated might be publicly available for synthetic data. I doubt that. I have my doubts that. I strongly doubt that actual data will become available easily. This is extremely valuable to companies, and it's probably not going to be easily accessible. I'm gonna say it this way.
All right, we are going over time. So thanks so much, Dr. Benoît. I'm sorry.
My pleasure.
It was very happy to have you here. It was very informative. Yeah, that's it.
My pleasure. Thank you so much for having me. I hope you enjoyed the talk.
Yeah, for sure.
And I hope to see you in the future in real life.
Okay. Yeah, me too. Thanks so much.
No problem.
And thank you everyone for joining us.